Hariom. Now we are going to discuss a new term called escape velocity. Velocity required for escaping from the attraction of a planet. Now you see from this one, this is Earth, and I am throwing a body up. If I throw it with a small speed, it goes to certain height and falls back. If I increase the speed again and again, I can see that it is going more and more higher and but still coming back. But if I throw with a particular greater velocity, the body moves and just goes out of the gravitational field of Earth, or it is escaping from the attraction of Earth. It won't come back. It is free from the attraction. So each and every planet will be having its own velocity of escape from its surface. That is what we are going to discuss in this one. So first of all, definition for escape velocity. It is the particular minimum velocity with which an object must be projected from the surface of Earth such that the body just go out of the gravitational attraction of Earth. This is what you call escape velocity from the surface of the Earth. So here I am having a mass m and I am projecting it with a velocity equal to escape velocity from the surface of the Earth. Then the body goes and goes up, decreasing its speed and just manages to cross over here. So when it just reaches over here, what happens is that its velocity becomes what? 0. So just to take this body up to this particular point, what is the minimum velocity required for that from the beginning is called escape velocity from the surface of the Earth. More than that, if you get, it goes from there. So we can only calculate the minimum using the equation. Now how we can derive an equation for this escape velocity? For that we have to consider a condition here. Here part of the motion will be inside the attraction of Earth and the other part is there outside the attraction of Earth. So force equation won't play any role here. So if you are confused with, then we will be depending on conservation laws, and here I am using the conservation of energy for getting an equation for escape velocity. That the total mechanical energy of the body when it is just projected from the ground will be equal to the total mechanical energy when it is just going out of the attraction of Earth. So if you equate those two, you will be getting an equation for escape velocity. So total energy of the body when it starts from here will be kinetic energy, then plus gravitational potential energy on the surface of the Earth means when R on Earth, let us take it on Earth, will be equal to kinetic energy plus gravitational potential energy at infinity means outside the attraction of Earth. Here, this is called infinity point. Okay? Now you write this equation. Already studied this one. That is kinetic energy of the body half mv square, and that v is v escape square. Then gravitational potential energy plus minus g me into m divided by re, because it is starting from here, the moment of starting, distance is re. Then will be equal to the same thing at infinity. The kinetic energy will be half m into 0 square, because velocity when this crosses the will be 0, plus minus g me m divided by infinity, the distance. So this is the conservation equation applicable for this case. Now you can see the right hand side, kinetic energy is 0. Now anything divided by infinity, that is also 0. Therefore, you will be getting half m v escape square minus g me into m divided by re equal to 0. Simple. Then half m v escape square will be equal to g me m divided by re. This is a very important relation. And from this one you get v escape from the surface of the earth will be equal to root of 2 into g into me divided by r. This is the equation for escape velocity from the surface of the earth. This can also be written as v escape is equal to root of 2 into g into re. That is in terms of acceleration due to gravity, and this is in terms of gravitational constant. Now here also you can see the escape velocity does not depend on the mass which is escaping. It's a very important thing. But it depends on mass and radius of the planet from which the body is escaping. So for any planet, if you want to write the equation for escape velocity, just consider its mass and radius in this one. Here I have written it for Earth, but you can use the same for any other planet. Only change is coming there for mass of the planet and radius of the planet. Now remember, this is very important, energy conservation. The force zero point is called point at infinity. In the beginning, gravitational low. From that low we found the gravitational force will be existing up to infinity, and at infinity the force is zero. So at what distance the force is zero, that distance is called distance to infinity. Okay? So these are the things related to what you call escape velocity. And before finishing, one more point I will say. If we send the satellite weight more than the escape velocity, you can see that this body reaches over here, but it won't stop there. It is moving out with a certain speed because you have given more than what is required to reach there. That is very important. So that is why the definition it is given that it is the particular minimum velocity. That's the definition we have. Particular minimum velocity with which the body must be projected so that it may just go out of the gravitational attraction of the planet.